Ions cross the neuronal membranes. Even if this transport, referred to as passive, requires no energy, forces are required to move the ions. What are these forces that make the ions move across a cell membrane? One of the two forces that make the ions move is the one due to the concentration gradient. Because molecules always move from the compartment where they are in a higher concentration to the compartment where they are in a lower concentration. For instance, for potassium ions, they will move from the intracellular compartment to the extracellular one due to their concentration gradient. They will exit the membrane. And sodium ions, they will move in the opposite direction because they have an opposite concentration gradient. They will move from the external compartment to the internal one due to their concentration gradient. Calcium also will enter due to their concentration gradient, and chloride ions will also move from the external compartment to the internal compartment. The second force that makes the ions move is due to the electrical gradient. It turns out that the plasma membrane is more negatively charged on the inside than on the outside. And for this reason, the ions will move because ions are charged particles. So sodium ions, for example, will be attracted by the intracellular side because plus charges are attracted by minus charges. So, due to the electrical gradient, sodium ions will have a tendency to enter the neuron. Potassium, too, it will have a tendency to enter. Calcium ions, too, because all these are positively charged ions. And chloride ions, it's the contrary. It will have a tendency, due to the electrical gradient, to move out the cell. How do these two forces, the concentration gradient and the electrical gradient, combine? This is what we call the electrochemical gradient. Now we have the two forces simultaneously. The one due to the concentration gradient in red and the one due to the electrical gradient in blue. How do they sum? For sodium ions, it's very simple because the two forces go in the same direction. So here the resultant force means that sodium ions will enter the cell. It's the same for calcium ions. The two forces are in the same direction. It's more complicated for the potassium ions and the chloride ions because the two forces are in opposite direction. To know in which direction they will finally move and at which potential, we have to first identify the membrane potential at which the potassium or the chloride ions do not move. It means that their net flux is zero. Here is the Nernst equation. The Nernst equation gives the equilibrium potential of an ion. And at the equilibrium potential, the net flux of this ion through an open channel is null. And it depends on the ion nature and concentrations. So what does it say here, the Nernst equation? It says that equilibrium potential of an ion in millivolts, it's a potential, equals RT over ZF, natural log of the outer concentration of the ion over the inner concentration of the ion. R is the constant of ideal gas. T is the temperature in degree Kelvin. Z is the valency of the ion, and F is the Faraday constant. So if we now make all the calculations, we obtain that the equilibrium potential of an ion equals 58 over Z. Z can be +1, +2, -1, depending on the ion. Decimal log of the outer concentration of the ion over the inner concentration of the ion. What is the value of E ion for each of the ions that we have seen at the beginning of the course. If we were to calculate for the concentrations provided at the start of the course, we would see that the reversal potential for sodium ions is plus 58 millivolts. It says that at plus 58 millivolts, the net flux of sodium is null. For potassium ions, the equilibrium potential is at minus 97 millivolts, for calcium ions at plus 121 millivolts, and for chloride ions, minus 59 millivolts. Here, the three top potentials are never seen in reality in neurons. The membrane potential never goes up to plus 58, never goes down to 97 millivolts, and of course never goes up to plus 121 millivolts. So it means that these ions never change directions. The sodium ions will always enter the cells, the potassium ions will always exit the cell, and calcium ions will always enter the cell. It's much more difficult for chloride ions because the equilibrium potential of chloride ions is very close to what we call the resting membrane potential of neurons. So we will see later how these ions move. Let's apply the Nernst equation to potassium ions. We suppose that only the potassium channels are open in this membrane. So sodium, chloride, and calcium ions do not go through the membrane. Only potassium ions go through the membrane. You remember that here you have 140 millimolar and outside 3 millimolar. And the membrane potential is minus 60 millivolts. Since the equilibrium potential of potassium, also called reversal potential, equals minus 97 millivolts, it says that the potassium ions will go outside until the membrane reaches minus 97 millivolts. Why? The exit of potassium ions hyperpolarize the membrane. It make it go from minus 60 to minus 97 millivolts. Why? It's because here potassium has a plus charge, so plus charges are leaving. So here there is a deficit of plus charges, so we can write it as if you gain minus charges. So the inside of the membrane is more and more negative than the outside until this movement of potassium ions stops. Why? Because when it reaches the equilibrium potential, the concentration gradient equals and is exactly in opposite direction to the force to the electrical gradient. The plus charges are attracted by the minus charges here. So what happens when potassium channels open? Potassium exits, and this stops when the membrane potential equals the equilibrium potential of potassium ions.